everybody is in. Okay, so we start today in earnest, the topics. And there is somebody I need to admit. And so before we do that, any questions from last time? Any doubts? Any comments? I suppose the protocol is, unmute yourself. And if you have a video also, then turn on that video too, so that everybody can see. It becomes a little more personal. Otherwise, it seems like we are all speaking to a wall. So if you have something to say, turn on your video and unmute yourself. Okay? Anybody? No comments? Nothing to add? We can begin?
Sounds good.
Okay. All right. Thanks for responding, guys. Otherwise, it seems like I don't know if my voice is reaching you guys or not. This is pretty new for all of us, I think. Let's see. One more person wants to come in. Okay. So, couple of things, bookkeeping stuff, announcements. I posted the link that we will be using throughout the semester in the announcement section of Lovelyma, and I sent an email as well. So since I'm encouraging you to sign into Lovelyma while we are Zooming so that we can do the chat through there, one of the advantage of doing with that is that even if the meeting is not on, you can sort of use that as an office hours. So if I notice it, I'll respond it right away or bring it up in the class. For the Zoom, you have to be on, right? You have to turn it on. In Lovelyma, it'll stay there. Okay, so that was one announcement. The second is that if you look at the schedule, I did not put any exceptions in that. So there may be some Mondays or Wednesdays or Fridays, there may be holidays, but it'll still show up. If you're using your calendar, it might still show up. But ignore those, because when I was scheduling it, I didn't bother to look through, creating exceptions as to which days were holidays. But I think that will be understood, right? We'll know them as they come. That was another. And people are still, hang on, admit all. Okay. I suppose this is like a typical classroom, right? People are still walking in.
Yeah, I think there's a way for you to set it up to where they can automatically just enter and you don't have to manually let them in.
Is it?
They came up this morning in another class, but I didn't look into it to see how it was done, but it was told it is possible.
It is possible. Okay. Thank you, William. I'll look into that. I think that would be better, because otherwise I have to keep looking in that direction, in that window, to see if anybody's waiting.
I thought you sent an email out where the Zoom link that you recently sent required a password, but when I came into this Zoom link, it didn't prompt me for a password or anything. So usually they put passcodes because so you wouldn't have to admit people yourself, but this Zoom link also just didn't require a passcode, it seemed like.
Oh, really? I thought there was an ID number and a passcode to it below that.
This definitely an ID code, I'm sure, but I didn't have to put a passcode.
Passcode? Okay.
I think that's part of the same settings system where when you go into that options, you can ask for the password because there was one in the email, or manually let people in. I don't know if you can turn them both off or what. But.
Yeah, let me take a look. I'm doing it for the first time, these details. Okay. Okay, thank you guys. These comments would always be helpful. Send me an email too if you notice anything that we need to do to improve it. So the sooner we do it, the better. I'm open to. All right. So I had put one file in resource section, and I call it RA, reading assignment. I couldn't think of anything else. It's not a homework. It's something that some people ask me, should I be reading in advance and what should we read? So I said, okay, maybe I should put something in there that we will be talking about chapter 1, and pretty much all of chapter 1. Hopefully, it depends on how things go, how slow, where we divert here and there. It might take a couple of lectures to finish chapter 1. Usually in face-to-face it does, because we end up talking some interesting stuff as an intro. All right, now let me get to talk about Silicon in general. And I want to try to make it interactive, so please respond. If whatever, as if it is a classroom, try to model it as a classroom if we can. How many of you are sort of familiar with semiconductors in general? From common knowledge. I'm not talking about technical stuff. I'm talking about, you must read some articles. Oh, Intel has come up with a processor that is, 14 nanometer processor or 14 nanometer process, or people are working on 7 nanometer process. And do you guys, you're familiar with some of that, the terminology, what those processes are? I see some hands. So when you think of the history of silicon or integrated circuits, do you know a little bit of the history as to who was the first guy who invented the transistor, and when did the first integrated circuit was made? Anybody knows who invented the transistor, which is a building block of an integrated circuit? I'm sure everybody knows that integrated circuit means there are lots of components on a chip, right? Integrated. A lot of different components are on the chip and they're connected to form a circuit. The difference between integrated circuit and a discrete component would be as if if you have a single transistor, in your lab you have a single transistor, one transistor that you connect somewhere. So that's a discrete transistor. And if you have multiple transistors, and that requires a very different process, of course, compared to making a discrete transistor, a complicated process. It's a planar, that if you have many of them on a chip and they were connected to form a circuit, as if like you were doing a 211, connecting your resistors, capacitors, transistors, diodes, all of that on a silicon chip, then that would be an integrated circuit. So just to get a little bit of inspiration from all of this, the transistor was invented. This is what I mean by that I divert. And because it gives us a perspective of where we are. Transistor was invented in Bell Labs, AT&T Bell Labs. Okay, and Shockley, if you might have heard of the name Shockley, William Shockley. Shockley was one of the guys Bardeen, and Breton. These are the three guys who are credited with the invention of the transistor. But the invention of the integrated circuit, which is totally a different ballgame in terms of putting all these components together on a chip, was done in Texas Instruments. And the guy's name who got credit for it, there were a bunch of people. Have you heard of a company called Fairchild? You might have heard of Fairchild. It used to be. So Fairchild was a semiconductor company, one of the original semiconductor company. So there were people like Robert Noyce, and from Texas Instrument, there was a guy named Jack Kilby. And Jack Kilby is considered to be the inventor of integrated circuit. And the year that it happened was late 50s, around 1958. So, and of course, all of these guys got Nobel Prize. Shockley got Nobel Prize for inventing. Jack Kilby got a Nobel Prize. Even though he invented it in 1958, he got a Nobel Prize in 2000. Imagine, I mean, how long it took. So, 2058 is how many? 42 years? 42 years later. So as it goes with these Nobel Prize guys, when it happens, they probably don't realize how significant it is. Only 40 years later, they find that the whole world runs on integrated circuits, so it has some value. Anyway, so Jack Kilby was a guy who invented. Now, do you know who came up with the first microprocessor? I'm all referring to silicon because I'm going to connect to these processes that you hear. Who came up with the first microprocessor? Which company? No? Are you curious to know which company came up with the microprocessor? Yes, no, maybe? Intel came up with the first microprocessor. And I think it was called 4004. And of course, it was something that you could use, and it was absolutely an invention because now you can make a calculator, So you could add 2 plus 2, and essentially it was acting as a calculator. That was pretty much the application that one of the applications that the first microprocessor found. Anyways, coming to what we in common sort of knowledge when you read about things or news articles or when you see it on the news, you might hear, oh, Intel has come up with a 7 nanometer process, or they are making a fabrication sort of facility that is 7 nanometers. Nanometer is 10 to the power 9, right? 7 times 10 to the power minus 9. That's a nano. Nano is 10 to the power minus 9. Can you imagine if you go back to 1971, the process was typically 10 microns. And a micrometer is 10 to the power minus 6. So 10 micrometer to 7 nanometer, you can imagine the amount of jump. That's 4 orders of magnitude jump in that value itself. Why is it significant? Well, initially, when we said that the process in 1970s was 10 micrometer, what it meant was that on a chip, the line width that you could define, the smallest line that you can make, which would either act as an interconnect or become a transistor, part of a transistor, the minimum line width, you couldn't go any smaller than that, was 10 micrometer. Okay, so, and that was in 70s. Now, if you need a line, an interconnect running from one end of a transistor to another end of a transistor, it can be though this is not 100% sort of considered this way now because things have gotten much more complicated. But think of it like a 7 nanometer is the minimum line width, which is not strictly true because, from it's become more complicated, but that's a rough idea to get a rough sense. So what does that mean? That means that we have been able to shrink the size from 10 micrometer to 7 nanometer, 4 orders of magnitude shrinkage in size. Okay, so all the circuit components, we have shrunk it from being large on a chip area, taking a lot of real estate on the chip, to taking very, very small area for the same functionality, for the same function. So effectively what that means is, it's like saying, I have 10,000 square feet of land, and earlier we could build only one house on that. So that house on a 10,000 square foot land was the limit. I mean, our technology was such. Now we can build on that same 10,000 square feet land, we can make thousands of houses with the same functionality and the same, obviously, you get the idea that now what a chip could do in 70s, if you made one chip, the same thing, you could make thousands of them in the same real estate. So that means that you can sell them cheaper because the cost of making it doesn't change a whole lot except for the capital equipment. Your fab has to be different and you have to get sophisticated instruments, but you're consuming less real estate. So by shrinking the size, for one, you're getting more chips out of the same process, because you're getting the same functionality in a much smaller area compared to what it used to be before. And the size shrinks. And what is also very interesting is, with the shrinking size, the speed of these chips goes up, meaning the speed of the circuit goes up. So consider going from 10 micron process to a 7 nanometer process. They've come a long way. And this has really created a revolution in electronic industry, right? So practically everything that is electronic has a chip in it, and it is made using some of these complicated processes and circuits. So this is the revolutionary thing. Okay, now sometimes I use this example. 10 micron, you may not sort of get a physical sense of, how big is 10 micron? I can understand an inch, how big an inch is, or 1 centimeter, I can 1 millimeter, I can see on a scale that it's very tiny. But how much is a 10 micron? 10 micron is, if you compare it to your human hair, on an average, human hair is about 50 micron in diameter, 50 micron. So your hair diameter is about 50, roughly. It can range from 50 to 100 micron, depending on how thick your hair is. But on an average, let's say 50 micron. So the dimensions in 1970s were 10 micron, which is 1/5 of that. So that itself is very small, right? And then now imagine 7 nanometer. So shrink it down by another 10,000, 4 orders of magnitude, shrink it down. So clearly, these things you can't see it with naked eye or even with a common microscope. So it's silicon. It's all done in silicon. And that's why we need to understand what's going on, how it is done. This course is not about processes as to how they are made. It's more about physics. What is this solid all about? Why is it important? Now, let me. I think if you have not seen it, let me show you. I just pulled up some Google search in case. Normally in the classroom, if we did face to face, I have these real stuff in my hand and I pass it around to show you. So, but I thought maybe I can show you what it looks like. And in the context, maybe just talk about how processing is, how the sequence of things, how it goes. Do you know where silicon comes from? No? From sand. And in Hawaii, we have plenty of it. Sand is silica, right? So you start out with sand and you have to purify it. Of course, it goes through, complicated set of process to purify to sort of get silicon dioxide out of it, and then to remove the oxygen and purify silicon. By the way, the silicon that is used in integrated circuit is the purest form of element ever produced, man-made purest form of element. So the purity of it, if you were to say, okay, what is the purity that is needed for integrated circuit of silicon? Then you would say 99.9999. It's called 11 nines. Typically, it's called 11 nines. 11 nines is 99, and you add another 9 of those nines. So when you write 11 nines, you put a dot at 99 point, that's the level of purity that is needed, or better. That or better. So you can imagine the purity of silicon. I mean, you cannot tolerate impurities in it. So you start out with sand, and of course it goes through various processes. And we'll talk about this crystal stuff, but it has to be made in crystalline form. So the way it is done is that you take these purified silicon and put it into a crucible, and you heat the crucible so that silicon melts. And it takes a huge amount of temperature. Silicon melts at over 1400 degrees Celsius. So in a crucible, it's a molten silicon. And then it's called a Cherkolsky method, and you pull an ingot. It's called an ingot, and it comes out. Let me show you what it comes out as. Has everybody seen a silicon wafer? Some of you have seen silicon wafer?
No.
No? Okay. Let me show you. Let me show you first what a silicon wafer looks like then. Okay. Can you see this? Can you see the page?
Yes.
Okay. Now, this is, any of these. This is Google. You simply Google silicon wafer and click on images. So this is a wafer. See how they look? It's a circular disc. These are typically very thin. So these are wafers. So here you can see a bunch of wafers that are stacked together. So this is a silicon wafer. Now, you don't make them as silicon wafers per se. During the purification process, it comes out as what is called a boule. So here I have just saved some Google pages. So it looks like this. So this figure is actually how, let me click on it and see if it, no, I don't want that. Oh, okay. No, okay. Can you see this? Can you see my mouse?
Yes.
Okay. Now, this is the molten purified silicon. And what is done is you lower a single crystal thing, and then you pull this out. And as it is being pulled, it solidifies, of course, because the temperature drops. And if a temperature drops, it crystallizes and it becomes, a solid. From a liquid metal to it becomes a solid. So this is called a boule. So when you pull it out, it looks like this. If you can see my mouse, it looks like this. and then, or a cut piece. So this is, a portion of it is cut off. So it's the boule, this is the boule that is solid silicon. And then you slice it as if you're slicing a loaf of bread. You get, as you slice a loaf of bread, you get these slices out of it. So when you do that, that's when you get these wafers. So from a boule, you cut pieces out of it, and you get, of course, hundreds of them from a single boule. So that's what you get as silicon wafer. Okay. I'm diverting a little too much, but I think just to get a perspective of what we are talking about when we say wafer, when we say,
Do
die.
they polish those wafers, and how do they do that?
Sorry?
Do they polish the wafers, or
Yeah.
What is the finishing process?
Yeah, finishing is polishing. So exactly. So you cut it, and then you polish it and clean it, and a lot of the details go on. And we're not sort of getting into the process part, but polishing, it's called polishing. So it's polishing as well. Okay, now, and here's a picture of it as to initially when the technology, I don't know if I click on it, if I'll get a, okay. So you can see that with changing, well, North America, no, that's not what I want. Okay, the idea here is that initially it was difficult, of course, people were trying to figure out that initially you could get only 2-inch wafer. The ingot, the boule was only 2 inches. Then, of course, more technology improved and things became better and better. Now you can get a 12-inch wafer. 12-inch, imagine, a foot in diameter. So it's a massive piece. It's like a plate. Okay, now, would you believe, or if you don't know yet, and this is a single wafer that somebody is holding it with tweezer, that the circuit that is made on this lies only in the top few microns, 5 micron. Though the wafer is maybe 500 micron thick or 200 micron thick, the circuit lies only in the top layer, or the devices lie only in the top layer. So you might say, oh, why do we need such a thick wafer if the circuit is made only in the top few microns? The answer is mechanical stability. So if you didn't have a thick wafer, you would blow on it, 5 micron thick wafer, if you blow on it, it'll fly away. So you need mechanical stability to handle it and put it through process. So the remaining part is simple for mechanical stability. Okay, now, so you get a sense of what a wafer is. Then on the wafer, actually, this is a good picture. You can see that after the processing is done, you get various chips. Each square is a chip, okay? And that chip is identical to the one next to it. So you're making hundreds of chips on a single wafer, okay? And that chip is actually called a die. First, it's called a die. So, and then you use laser to cut these single dies out. And then once you put it into a package, then actually you begin to call it a chip. So when you cut it out, it's called a die. Now imagine from a processing point of view that when you're processing, you're not processing a single wafer. You're processing a whole group of wafers. You're processing a whole cassette. Imagine you're processing a cassette like this, and each one of them has hundreds of chips, and then you have hundreds of wafers. You are creating thousands of chips in one go. So you can see how the more you make, the larger the wafer size, the more chips you will get out of it. The smaller the chip you can make, meaning miniaturization from 10 micron to a 7 nanometer process, the more chips you will get out of it. This is what leads to reduction in price, because the process is the same, pretty much the same, except the capital, more sophisticated equipments are needed. But you are creating many more chips at a the volume scale which you do. Here I have a picture of a die. So notice that this is, if you look at this, you can see it's the same wafer, but you shrink the size of a chip. The functionalities may be the same, right? You're shrinking the size. So functionalities are the same, but here you get only here you get relatively fewer chips compared to here and to the next one if you shrink the size. So this is just an example. And I'm not particularly sort of looked into, if you just Google and you say silicon die and then images, you'll get bunch and, these are no specific sort of value. Some of you may be wondering why the different colors. Anybody knows why different colors? Are you curious why they are showing different colors?
Is it the reflection of the light?
Reflection of the light. There are various layers that go on the chip. So, right? So in making a chip, there are several processes, and it involves putting different layers, insulators, then conductors. And so when you start stacking them up, effectively, the refraction from those leads to different sort of light. So it's these different colors. So don't think that these are these are artificial colors. This is simply because of what it is. Okay. Is there anything? By the way, so when you pull out this chip, it becomes a die, and then it goes into a package. So now this is something you must have seen, right? If you look at this, if you follow my mouse, if you look at this, actually I can use a pen because I bought a pen especially for this kind of stuff. Oh, okay, I can't do that on a web page. So,
Professor, did you see the question in the comments about are the layers stacked?
I'm sorry?
There's a question in the comments. Let me pull it back up. Are multiple layers stacked? I don't know that.
Yeah, multiple layers are stacked. There are various deposition processes. So you might have a conductor, then an insulator, and then a conductor on top of it, and then another insulator. So these are all stacked up. Okay. I don't have that window of comments. Okay, any other question? Okay, now this is if you look at this, these are just some bunch of pictures. By the way, this is printed circuit board. This is not a chip here, but this is a chip in a package. So the die sits inside this plastic package. It can be plastic, it can be ceramic. So I'm sure you've seen things like this, right, on a printed circuit board. But the die is inside of it, which is made out of silicon. So, and it's a very interesting process as to how the die is connected to the package. It's called wire bonding, and there are very thin wires that are used to bond from the chip to the package and then to the external pins. It comes out of the external pins. I'm trying to look at if there is any wire bonded chip here. It is okay. Yeah, if you click on wire bonding or something, you'll see. Yeah, here. If you look at this, these are the wires. So this is a chip, and these are the wires. And this is, of course, all automated process. And this goes to a package, the pin on the package. So that's how it connects. So it can be aluminum wire or it can be a gold wire. This is a good example. You can see how complicated these wires are going out to the package. The chip is sitting inside and the package. All right, I think that's what I wanted to give you an idea of, that when we talk about Oh, here, this is a good example. This is not an integrated circuit. Somebody must have made a device, but this is what the wire looks like. This is a gold wire. Okay. All right. So any questions before we get into chapter 1? If we talk about wafer, chips, die, processes, at least we have a sense.
Sorry, I just had a quick question, Professor. Will you
Oh.
be recording our class by chance, just so that as we go through, I can refer back or anything like that?
I am not recording right now. I have to give a thought to it. Maybe I will. I know somebody else had brought that up last time too, but let me think about this. Give me a little bit. None of this that I'm talking about is going to be part of the quiz. This is just to get a sense of what wafers are, dies are, so that we are familiar with the terminology that might, might come up as we go through. Okay, let me think about that. That question was asked last time too. So, okay, let's say stop share. Okay, now, chapter 1. I'm using slides. Normally I use Blackboard, so I'm using slide from one of our colleagues who taught in summer, and he was kind enough to share it. So these are his slides, but they are pretty good. So whenever I find these are good slides, I'll use them. Okay, so what is this chapter about? Remember last time we said that that structure has huge impact on electrical properties. And so we need to at least understand what does that mean? So this chapter is about crystal structure of solids in general, and specifically we'll talk about semiconductors too. Now, so when we think of semiconductors, remember last time we said that if in terms of electrical properties, if we were to classify based on electrical properties, then we would say that a solid could be a conductor, a semiconductor, or an insulator, right? It's one of these three. And of course, conductivity is the term that we use. A conductor has high conductivity, an insulator has low conductivity. Now, so we have some common examples we know already of a conductor, like a copper is a good conductor. Insulator, we already know, what are good insulators. Plastics, wood, all of that don't conduct anything. So, and semiconductor is the interesting solid. Now, in semiconductor, you can break it up into two sort of broad categories. One is elemental semiconductor, meaning it's an element, single element. Single element meaning silicon, germanium. Carbon is not necessarily, it's a conductor, semiconductor, but in our integrated circuit sense, we are not going to sort of use this much. But you will hear more in silicon and germanium, but carbon, not so much. What is interesting is they come from the same periodic table, same grouping in the periodic table. So that's column 4. So that's elemental. Now, I'm sure everybody has heard of silicon. You may also have heard of germanium. Have you heard of compound semiconductors? Is it being shared? Can you see this? Oh, oh, wait. You should have stopped me. Okay. So, all right. So interrupt and stop me if you think something is not right. I was looking at these slides. Can you see this now? Okay.
Yeah, we can see.
Yeah. So elemental semiconductors, as I was talking about, are from this grouping. Silicon, germanium are common semiconductors here. And then we have, and all of you have heard of this. Have you heard of compound semiconductors by any chance? How many of you have heard of compound semiconductors? No? Okay. It turns out that there are a lot of compound semiconductors, meaning a compound. Chemically, it's a compound. It's not an element. Gallium arsenide, this is pronounced as gallium arsenide. Aluminum arsenide, aluminum phosphide, gallium nitride, gallium phosphide, indium phosphide. These are all semiconductors. And they're called binary semiconductors. Why binary? Because they involve two elements, gallium and arsenic. Take gallium and nitrogen, gallium nitride. So there are two elements to it that make this compound semiconductor. Then you have ternary. If you have three elements, and examples, these are simply examples. Aluminum, gallium arsenide. Aluminum, gallium arsenide. This is also a semiconductor. Indium, gallium arsenide, also a semiconductor. Blah, blah, blah. You carry on. This grouping, of course, is not element, right? It's compound. What you notice here is, in this particular case, that gallium comes from column 3, arsenic comes from column 5. Aluminum comes from 3, arsenic from 5. So the grouping here typically is that of 3-5 compounds. So these are called 3-5 compound semiconductors. This whole group is called 3-5. They can be binary or ternary. Okay. Now, this is an expensive technology, and we'll talk about applications before I get through this slide, after I get through this. Now, what is interesting is that you can make a compound out of silicon and germanium as well, and make a compound semiconductor. Now, why would one do that? There are details, hopefully, that you will, learn more and more as you understand more and more semiconductors down the road. Not in this class, but I might mention a few things. So this would be a compound semiconductor as well. Now, silicon is, what is the correct word? The bread and butter of electronics integrated circuit technology. Silicon is cheap. A very large fraction of electronic stuff is made out of silicon. Okay, very, very large. So it's the bread and butter of IC, of electronic technology. So you might say, where are these guys used? Where would you use them? It turns out that silicon is good for electronic application. These guys are good for optoelectronic application. So say, for instance, if you wanted to make a laser, solid state laser, like you have your pointer, right? For your PowerPoint presentation, you have a pointer. The chip that is sitting inside that is generating light, which is 1/10 the size of your hair, the dimension of that thing could be 1/10 the diameter of your hair, a small thing, and emitting as strong a light for your pointer is made out of these guys. So these are good for making light emitters, LEDs, lasers, solid state lasers, fiber optic detectors, blah, 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 bunch of other things. But in general, if you were to say, okay, what is it that distinguishes this from that? You would say, these are very good for optoelectronics. That's one. If you needed very high-speed electronics, okay, extremely high speed, perhaps in military applications, and of course, I'm talking about when I say optoelectronic, I mean infrared cameras or night vision stuff. All of that comes from here. Then you might also use some circuits, try to make circuits in compound semiconductors, because these electrons can move much faster in these semiconductors than it can in silicon. So very high-speed electronics, microwave, you might have heard of MMIC, millimeter and microwave integrated circuits. A lot of them can be made in gallium arsenide. There are people trying to actually use light to make chips, where you can manipulate light on a chip level, not just electrical voltages and current. So optoelectronic ICs people are trying to, essentially for optical computing. A lot of research goes on in this area. Okay? All right. Any questions on this?
I think slightly off topic, but related. Somebody asked in the chat if you were planning on sharing the slide deck.
I can, yeah. Yeah. I think I'll ask the author or who made the slides and see if he's okay with it, but I wouldn't have any problems doing that. Okay, so semiconductors are all, of course, solids. And so we talked about from a conductivity point of view, we talked in terms of application point of view, but structurally, what do they look like? Okay. If you take a bunch of atoms of a solid and make a gobbledygook out of it, then the atoms might look like this, right? They might stick to each other in no particular order. The main thing is to see that there is no particular order. They are sort of just, put together somehow. This is called an amorphous state. The key here is that atoms don't take any order. There is no ordering to the atom. As opposed to a crystalline state where the atoms, the solid is formed, where the atoms go to very specific locations. Okay, it's not like a hodgepodge like this. Okay, so this is crystalline solid, and it could be the same material. This could be silicon. It will be called amorphous silicon. This is also silicon, but in a crystalline format, and this could also be silicon. Now, in this, it's called polycrystalline, where some portions of that solid might have crystal-like ordering, but then, it's not, the whole thing is not a single crystal. It's broken up. So these are called grains. And the grains are put together, and between the grain boundaries, or between the grain, there is no particular order. So those are called polycrystalline silicon. So they can be the same material, but in different forms. Okay, so amorphous is solid and it's placed randomly. Crystalline are periodically ordered. So this is how we, now for application point of view, each one of them has different application. Each one has different sort of process related issues. But for integrated circuits that we are going to be limited to is we are looking at crystalline solid. So we want crystals. Solar cells can be made out of this, solar cells can be made out of this, and solar cells can be made out of all of them. But for electronic circuits that we are talking about, like what goes in your memory chips, your microprocessor, it's single crystalline silicon. Any questions? Okay, I think we have just begun. Maybe just let me stop here and give you some time to. Oh, somebody is waiting in the room. This is a problem. I have to figure this out. I don't know how long he was waiting. Okay. Now, what I wanted you to do is in 1 minute, if you're logged into Lavlima, for attendance, I have to do this for the first week. After that, we won't be doing this. And I know last time you guys did it present, through the chat room. But in Lavlima, I created a quiz because are you present? Just press true. Click true. And then the nice thing about that is it just gives me an Excel spreadsheet right away of who was present and who was not. So please, if you're present, click on true. You are present, and that will help me. As I mentioned, there is some reporting requirement in the first week. If somebody doesn't show, then we have to report as a no-show. So we are going to do this just for the next 2 or 3 times, and that's it. After that, no attendance.
Did you say that it's a quiz, or where did you want us to put?
I'm not seeing it.
You're not seeing it?
Yeah, it's not in the quiz this way.
Yeah, it is in the testing. Okay, hang on. Let me just do it again. It's a very simple thing. Does it show up?
Give me a second. It's reloading.
It's up.
Okay. Yeah, I think somehow it didn't publish the last time I did it. So if you're present, just click true, and that creates a nice Excel spreadsheet for me. Okay. All right. So, any questions before we close? And if somebody mentioned that people don't have to wait. I'll try to do that next time so that you don't have to wait out, in the waiting. I don't have to admit, you can join in. So, because I feel bad for this particular one case that in the last minute, I saw still waiting to be admitted. So. All right, we'll see you on Friday.